My research is about finding new signatures for potential physics beyond the standard model. The standard model of particle physics is a framework in which all the currently known fundamental particles are incorporated. And this model has been probed extensively over the past 100 years. The Large Hadron Collider in Geneva, there is data being recorded by multiple experiments on very energetic collisions between protons and protons. And in these energies, all kinds of standard model particles can be produced, but also, or so we would hope, rare particles which exist outside of the standard model. And the context of my research is to analyze this data and to find potential hints in order to broaden our understanding of the universe, the fundamental building blocks of the universe, and also to explain some phenomena which are currently rather mysterious, such as neutrinos, the existence of dark matter, as well as an asymmetry between matter and antimatter. So my research is the model-independent multi-lepton analysis. So there's many theories as to what exists outside of the standard model. There's very little analyses that look at large data sets. There may be something that is interesting that was previously overlooked, and that can give us, valuable insights as to where the next searches should look, where the next data can be taken, basically what our most promising leads are. One important thing about general searches is that you have standard model backgrounds, as well as standard model backgrounds plus one fake lepton. So normally two protons collapse together, then a series of decays happens very closely, and this creates a lepton. But outside of this interaction point, there's also additional hadrons that decay later on, and then they turn into leptons, and they get protected as if they were leptons all along. And these we call fake leptons. And the fake leptons are rather tricky because it is harder to simulate them from theory first principles. We look at our expectation of what we expect the data to do, and then we compare this to the amount of events that we actually measure. And this is what I did for multiple regions, which together cover a large amount of the 3 lepton and the 4 lepton data that is available. 22 comparisons in total for this thesis. And then I've looked at, okay, do these correspond to what you expect using only the standard model? And the answer is yes. So within that, we know that the standard model functions well. There's some discrepancies, which if you look into them, they're either negative or positive. And these might either be because of statistical fluctuations, which means they're completely coincident. So we looked into those a bit further. So now we have 22 comparisons where we can tell, okay, this is all the models that we can now exclude, narrow down the burden that theorists have to, look at all the different models that they have. They can now look at, these results and they say, okay, this works, this might work in the future, and this does not work. So based on this, and of course, there are many other analyses, the next generations of searches can be devised for the future.